So as we continue our investigation of fluid statics, what we want to do now is find forces on inclined planes. Everything we've solved so far has been on vertically walled tanks, but many tanks might have an angle to them, such as this one here. And let's just go all the way for the end of this, which is, what if we wanted to find the force on a certain area? Say this tank has a cork in it, some sort of a round plug, and we want to find the force acting on that plug and the location that that force acts at. If you watched the derivations, you saw this, but if you didn't watch them, that's okay. The formula that we can use is that the reaction force is equal to rho g hc times the area. And this is really convenient because that looks like something we've seen before. You might be asking, what's hc? Well, every shape has a centroid. In this circle, it's just the middle, but triangles, of course, it's a little weirder, right? It's offset. And that centroid on the side of this wall is some distance below the surface of the fluid, hc. And so with just a little geometry, we can find the reaction force. And the beauty is this works for any shape. Now, where's that force acting? Well, we have a formula that looks like this. Yc is equal to Ixc over Yc times the area plus Yc. Okay, a little bit of translating needed here. First off, what is Yc? How about Yr? This is supposed to be the reaction force Yr. C's on this side of the equation. We want to know where this reaction force is acting. And the answer is it's acting at a distance Yr measured along the surface of the tank here. And so how do we find that? Well, this formula tells us that we want to use the second moment of inertia divided by the location of the centroid times the area of our shape, and then we add the location of the centroid to that to get us a distance measured along this surface. Looks a little inconvenient until you realize that these are tabulated, and so for example, for a circle, we can find my note here. There we go. We can find from the textbook some stuff that looks like this. So let me just move my most recent notes out of the way here so you can see this a little better. In the textbook for a circle, you would find a picture like this, defining some coordinates. The centroid is located at the center of it. And then we have the fact that the area is pi r squared. The moment of inertia looks like pi r to the fourth. And this one here would be the moment of inertia to spin it, and that's why it's a 0. This is like flipping it over the x or the y-axis, kind of the way it would rotate in a coin toss. And so we go look up these two values, right? Where's hc? Well, a little bit of geometry gets it, and that's it. The force is super easy to find. We just look up how to do the geometry for hc. We can see here it's located at the center, and so this problem would have to give us enough geometry that we could find this. Maybe they tell us the distance along the surface and we have to use an angle like theta. You can do some sines and cosines to find it. Or maybe they tell us directly that the depth of the center of our plug is so far below the surface of the fluid. To find the location of the force, say so that we could put a force to counteract it and stop it from moving, that's where the second equation comes in handy. And the trick here is picking which value of the moment of inertia to use from the table. And you have to imagine this circular plug is going in and out of the board here. And so it's trying to rotate about its x-axis. And so the moment of inertia about the x-axis is appropriate, and that's this one here. And so the reaction force, Yr, we're going to just sub in the moment of inertia, pi r to the 4 over 4, and that gets divided by Yc times the area. So Yc, that's the distance, by the way, along the surface to the centroid, Yc. The area is pi r squared, and then we're going to add to it Yc. And we can do a little bit of canceling here, so the r squareds cancel. This becomes r squared. Get rid of the pi's. And so we're left with Yr as r squared over 4yc plus yc. And so that's the location that this force acts at as measured along the surface. The key takeaway is that we're going to measure y starting at the fluid surface here and go down the wall here. That's y. H is going to be this vertical thing. And so there's a little bit of geometry to solve to make these problems work, but that's it.